We have things to do today. Uh, our knowledge of vector operations is going to pay off today. It's going to make things much easier for us now. The things that we were actually aiming for, which is discussing today lines in three-dimensional space, and then also planes in three-dimensional space, which are going to be much more useful to us than lines in three-dimensional space. And our knowledge of vectors are going to make those topics really easy, or a lot easier. Okay, so if we just can recall the things that we've learned about vectors and vector operations, it makes all these topics about lines and planes go really smoothly. So you notice there, a test is a week from today. Notice the answers now to the sample test are posted. So I posted those this morning. And but again, please look at the sample test before you look at the answers, right? So the answers are posted separately from the blank sample test. So work on the sample test first before you look at the answers. To make that sample test a little bit more digestible, because it is pretty long. Let me see if I can capture my here's the posting for the sample test there, right? There's a couple of these problems that are kind of lengthy and not not all that important. So I listed them as optional here on the sample test. In particular, this problem number 5 is really long. It's about a parallelogram, which really doesn't look too much like a parallelogram, but I think that is a parallelogram. And goes on like 2 pages because there's lots of questions about that. So and we're not all that really interested in parallelograms. It was just kind of an interesting application of some of our knowledge of vector operations. So I made that one optional. I mean, you can do it. It's the individual parts are not that hard, but there's a lot of individual parts, so that kind of makes the sample test a little bit lengthy. And so I made that one as optional. And then let's see, there's another one that's just a really straightforward. Well, I don't know if it's straightforward. It's a 2-vector question. Sorry, a 2-dimensional vector question. Where is it? Oh yeah, it's right there at the beginning. So this one is just trying to test your knowledge of 2-dimensional vector operations, and so but not all that important. So I made that one optional also, because it just to save a little bit of time. So again, you can do it, but it's not difficult. But if you're trying to save time working on sample tests, then you can drop those 2 optional problems. So you see, anyway, there's the sample test answers, right? Okay, and with solutions worked out for almost everything, unless there's a question where the solution is just obvious, or if it's late in the sample test, and I didn't want to show, for instance, the computation of a cross product because we had earlier examples of computations of cross products. So I may have computed a cross product and just wrote the answer down without showing the steps on some of the later problems in the sample test after the initial cross product problems, things like that. But for the most part, the solutions there are given. All right. Now, since we don't have too much time to review in class, what I will do is this weekend I will make a video of a Zoom video and post it on YouTube of the and the link will be on the Blackboard page of I'll just choose some of the highlight problems here from sample test, and I will discuss the solutions, okay, in a video. Right, not the entire sample test. That would take too long of a video, but just some key problems there, that that are either important problems that you really need to know how to do, or the problem has lots of parts in it that illustrate various facets of vectors, and so I think it's a useful problem to help you study for the test. Anyway, so I will make a video this weekend and post that. on the Blackboard page in that sample tests folder. But I'll send an email via WebAssign. I will send an email via WebAssign that is posted when that gets ready. So you can use that also to review before Wednesday of next week. Okay. So everyone understand all that? I've got questions about the test. So, so again, remember, you can bring your index card, right? Your survival card, that's what I call that. So you can bring your survival card with you. So if you want to write down important formulas, there's going to be a couple more formulas coming up here that might be useful to include on the index card, because as we get more vector formulas, they start running all together. They look a lot alike. So so a standard size index card. This is a standard size index card because it's one that you can purchase commercially, right? But this is also a standard size index card, so you can also use this, right? So as long as it's something that you buy and not make, then so okay. But not an 8.5 or 11 sheet of paper, because that's not smart. Right? So, okay. So you can bring that plus your calculator. Be sure you bring something to write with, right? Okay. So you guys are pros, so I don't really have to remind you too much of this, but in lower level classes, I get people showing up for tests. It's amazing they even have their clothes on. They don't have anything with them. So it's like, did you know you were taking a test today? Oh yeah. Did you think to bring a pencil? No. So anyway, so something to write with in your calculator and the index card. All right. So let's see. You guys turned in a homework on Monday, so y'all did really well on that. At least the scores are really high, so that's excellent. So y'all been doing really well on the homework. So of course that bodes well for the test, and that also means that your homework average is going to be high. So that of course that counts towards your final average, but also counts toward giving you some flux dollars, right? That you can use at the end of the semester. And if you get a high score on this test, then you'll really get a lot of flux dollars that you can use at the end of the semester, right? To buy either out of the final exam if you don't want to take the final exam, or just buy bonus points. So don't forget, those flux dollars will start accumulating here after the first test. Okay. So I'm done talking before the notes. Do y'all have other questions that you want to ask about before we get too far? Yeah, 15. Huh? Number 4 on, what was it? On the homeworks? On this one? No, on this one? On the cross products? Okay, let's look at that quickly. So number 4, that doesn't sound like that would be super challenging. Is that something that we didn't discuss? This one? All right. So this is actually an important problem. So this is a good one to just to pay attention to. Not because computing the cross product is all that challenging. Once you practice cross products, that should be pretty straightforward for you. But just the how we're using the cross product here, right? Okay, because it says find a unit vector. Oh, that's what's throwing you off, Fatin. Okay, it says find a unit vector that is orthogonal to both u and v. Okay, so and so this is going to come up again today. The way you find a vector that is orthogonal to 2 given 3-dimensional vectors. Okay, so you have 2 vectors, right? Okay, and then you want a third vector that is perpendicular to both of those given vectors, right? Okay, so you got 2 vectors. Show it. Picture it with my fingers here, and then you want a third vector, right? That's orthogonal to those 2 given vectors. Okay, that's going to be important today in when we're studying planes. because if you have two vectors, of course, vectors don't have a position, right? But you can think of the vectors as being coincident, meaning you can think of the vectors as starting at the same point, like my two fingers sort of do here, right? Okay. And so if you have any two vectors, as long as they're not parallel, that defines in three-dimensional space, that defines a plane, right? There's going to be one plane surface that contains the two vectors, right? As long as they're not, if they're parallel vectors, then that's a different story. But as long as they're not parallel, you have one plane that contains the two vectors. Okay, and then so if you find a vector that's orthogonal or perpendicular to those two given vectors, what you have found is a vector that is perpendicular to the plane that contains those two vectors. And that's going to turn out to be useful to us, having a vector that's perpendicular to a plane. Okay. All right. So that's where we're going to apply this fact. So to find an orthogonal vector here, you just take the cross product of the two vectors. That's all that you're being asked here. Okay. But Fatin, I think what caught you there is you didn't read the instructions. It says find a unit vector. When you find the orthogonal vector, it may or may not be a unit vector. So if it's not a unit vector, you have to turn it into a unit vector to give your answer, right? Okay. So I think that's probably what messed you up. Now, y'all have those? Did y'all write those two down for me? I'm going to switch to the notes. I mean, let's go ahead and compute the cross product here, since just as a reminder of how we compute cross product, since we were doing that last time, right? Let me switch to the notes here and see if I can find some. Let me switch to the notes here and see if I can find some blank paper. Almost. Let me add a piece. All right. So we had that. So those vectors called u and v are two favorite names for vectors. So what was the vector? What was the first vector u? Yeah, those are the three components. So remember, to compute the cross product there, I'm going to insert that vector as a second row of this table, right? Okay. The first row is going to be just labeled I, J, and K, right? The unit vectors, the three standard unit vectors, right, in 3 dimensions. So this is, this first row corresponds to the vector u, and then the second row is going to correspond to the vector v, right? In this little table I'm drawing, and this table is just a device, right? It's not crucial, but it's just a device to help me compute the cross product, right? What were the components of v? Yeah, 11, negative 12, and negative 1. So probably on your version of problem number 4, that these numbers are different, because I think these are randomly generated. But all right. So but the steps of the solution, of course, are the same. So to compute u cross v, right, which is going to be a vector. Remember, you play this little game, right? So you think of eliminating the first column, right? Okay, and then in the second two columns, you compute the cross product, right, of the two second rows, right, of the last two rows. So you would get what? Minus 6 times minus 1, right? Minus 6 times minus 1, which is positive 6, right? And then subtract off this product, right? 4 times minus 12, which is a minus 48. Okay, so you got lots of minus signs when you're doing cross product. So make sure you keep up with those, right? So you have a positive 6 minus a minus 48, and this is going to be multiplied times I. All right. And then you eliminate the second column, right? And do the cross product again. Except this one, the second cross product, you subtract, right? So let's see, what is that second cross product? Let me leave myself some room. So I have minus 8 times minus 1, right? Because we're eliminating the middle column, right? Minus 8 times minus 1, that's positive 8. And then you subtract off 11 times 4, which is 44, right? But don't forget, you subtract that cross product. And that is going to be then the coefficient of J in the cross product, right? And then finally, for our coefficient of K, you add that back in, right? And then what's that third cross product. There you eliminate from consideration the last column, right? And then you take the cross product of these numbers. So you get, let's see if we can do this. -8 times -12, what is that? Positive 96? And then subtract, you're always subtracting when you do the cross products here. So you subtract off 11 times -6, which is -66. Okay. Yeah, I see why this one is so annoying, because you come up with these big coefficients, right? So you have 54i, and then what's this? Inside the parentheses is -36, right? But you have this minus sign in front. So that becomes positive 36j. And then what do we have here? This big coefficient on k. It is going to be positive, right? What's 96 plus 66? Or how much is that? 162 or something like that? So 162 times k. Well, and so that is the cross product of the two vectors. That vector is orthogonal to these two vectors, but they wanted a unit vector. Okay, right. And this, I'm pretty sure, is not a unit vector. I don't think its magnitude is 1, right? It looks like it has a really high magnitude, right? That's a really long vector. Okay, so we have to convert that to a unit. We have to convert that to a unit vector, right? So you have to compute its magnitude. You have to compute its magnitude and then divide, right, this vector by the magnitude. That's how you find a unit vector in the same direction as a given vector, right? You divide the vector by its own magnitude. So we have to do this, right? We have to compute the magnitude of u cross v. Y'all are going to have to help me here. We don't have to simplify it. At least not. I'm not going to simplify it here on paper. I don't know what WebAssign wants, but I'm not going to try to simplify this big magnitude, right? So we have 54, the square root of 54 squared plus 36 squared plus 162 squared, right? The square root of that. And so we have to get out our calculator and calculate all these squares and add them all together. What's the final sum there under the square root? Y'all do that for me? $30,456. Okay, and all right, so doubt if that's a perfect square, or I guess it could be by luck, but just by happenstance. Don't think that's perfect square. I'm not going to try to simplify that square root by hand. All right, so did they want? They didn't want decimal estimate here. Oh no, I'm just going to leave it like this then. All right, so we would get here then as our unit vector u cross v, right, divided by the magnitude of u cross v. And so we get this really ugly expression. So 54 over this big square root times I plus 36 over this big square root times j, and then plus 162 over this big square root times j. And I hope that WebAssign will accept that as the answer and doesn't expect you to simplify these coefficients, okay? They could be simplified some probably, but that would require you to, by hand, simplify square root of 30,456. We could do that, but it would take us a little while to simplify this by hand. Do you know how you simplify this by hand without using the calculator? You want to try to write that as the product of perfect squares. So you would try to write this this quantity, 30,456, as the product of as many perfect squares as you can. All right. So one place to start is you can factor 100 out. Can you factor? No, you can't even factor 100 out, right? Is there anything you can factor out of this? 4? Okay. Does 4 work? Try that on your calculator.
Yeah,
Oh, 4 works. Okay.
times 7,000.
Okay, so there we've made progress. 4 times 7,614. And see, since 4 is a perfect square, you can bring that out as a square root of 4 is 2. So now you're down to 7,614. And now you're going to try to factor that more. Does a 4 factor out of that? No. Okay. Wow. 9? Don't think so. 9? Really? Oh, okay. So this is 9 times 846. Okay. So see, 9 is a perfect square, so you can bring that out as 3 times that 2 would be 6. So you have 6 times square root of 846. Now I'm going to try to work on see if you can reduce square root of 846. 9 again? Oh, so that means 81 would have divided in here to start with. Well, who knows, right? Who knew that? So it's 9 times what? Now, oh, now we're making progress here. 9 times 94. So I can bring again, square root of 9 is 3 times 6 would be 18. So you have 18 times the square root of 94. And there you're stuck because 94 is 2 times 47. And 47 is a prime number, I think. Okay. So, and it's not a perfect square. So that's it, right? You cannot reduce that any further by hand. So this is really 18 over the square root of 94. Well, that's convenient because so you could have reduced these coefficients, right? Because 18 would go into 54 3 times. Is that right? So you would end up with 3 over the square root of 94 times I. And then 18 goes into 36 twice. So you'd have 2 over the square root of 94 times j. And then I don't know about this one. Does 18 go into 162? 9 times? So you would have 9 over the square root of 94 times k. Oh, so see? Well, that's okay. That's a lot more trouble than it's worth, right? So, we can show off our our grade school arithmetic abilities here, but I'm not sure that that's I'm not sure that's necessary. It wouldn't be necessary for a test for sure, but I don't know what WebAssign's expectations are again for simplifying these coefficients. All right, Fatin. So what did you mess up on? Which part? Oh, the unitizing part. Yeah, you sent me this problem, right? And it looked to me like you were not computing the unit vector. Okay. All right. Let's look now at our let's look now at our nodes. Well, these are the nodes. So let me scroll back up here. And so remember last time we had discovered that a first degree equation in 3 variables, which is going to look like this in general form. If you simplify it and set it equal to 0, a first degree equation in 3 variables will look like this. The x, y, and z are the variables here. The a, b, c, and d are just constants that change from equation to equation, right? But x, y, and z are the variables in this equation. So now the reason I say first degree is notice all of the variables here, all of the unknowns, I should say, are raised to I'm not using the right terminology, which drives me crazy. These are all variables, but the unknowns in the equation are x, y, and z. Okay. All right. So, but all of the unknowns in the equation are all raised to the first power, right? And so that makes it a first degree equation in 3 unknowns. Okay. X, Y, and z. The terms variable and unknown are kind of interchangeable, but they do have a slightly different meaning in certain contexts. All right, so now remember, if you have a first degree equation in 2 unknowns, x and y, when you graph the solutions to that equation in 2-dimensional space, you get a straight line. okay? And we were wondering, well, okay, does the same thing happen in 3 dimensions? So if I have a first degree equation with 3 unknowns, if I graph the solutions to that equation in 3D space, do I get another straight line? Okay, in other words, the straight lines in 3 dimensions, are they kind of the same as straight lines in 2 dimensions? And the answer is no. That's what we discovered last time, right? Because if you look at a specific example, here's a specific example of course, this has 3 unknowns in it, right? X, Y, and Z, and it's first degree because the X, Y, and Z are all raised to the first power, right? If you start making the graphs of solutions to that equation, you quickly discover that don't have a straight line, okay? And an easy way to find solutions to equations with 3 unknowns or 2 unknowns is to look for the intercepts on the axes of those equations, or the graphs of those equations, right? So for instance, if you want to find the z-intercept where this graph crosses the z-axis, right, set x and y to 0. Well, when you set x and y to 0, you get z is equal to 6, right? So there's our plot of the z-intercept. And then you can also plot the x and y intercepts as well. So to get the x-intercept, set y and z to 0, right? That would give you x equals 6. Yeah, there's x equals 6. So I plotted that point. And then the y-intercept, set x and y to 0, you get a minus y equals 6, which means y is minus 6. So I plotted this point down here. That's the y-intercept of the graph of the solutions to this first degree equation in 3 unknowns, right? And notice those points do not fall on a straight line, okay? Those points don't fall on a straight line. So the graph of this equation in 3 dimensions is not going to be a straight line. Actually, it turns out to be, as we said last time, it turns out to be a plane surface, not a line, okay? And so if you connect these 3 points, and I think of that as being the piece, that little triangle as being the piece of a plane. I shaded part of that plane, but actually the plane extends infinitely to the left and right and up and down and below. Okay, so here's a graph of a little piece of the here's a little piece of the graph of the solutions to this equation, and it turns out to be a plane, and you can see part of the plane here in the picture. Does that look like a piece of a plane? Yeah, if you look at it properly, it does look like a piece of a plane that's tilted a bit, right? Okay, so so the moral of that story is we can't just it's not the case, unfortunately, that first degree equations are going to give lines in 3-dimensional space. Now, what actually does turn out to be true, and we'll get back to it in just a second here, is that first degree equations in three unknowns, right? First degree equations in 3-dimensional space, their graphs are going to turn out to be planes, just like in this picture. Okay, so so the graphs of first degree equations are not complicated. Okay, but they're more complicated than straight lines. Okay, you get a flat plane, not a straight line. Now, before we discuss that, though, why that's the case, we do want to talk about, well, how do we write down expressions for lines? How do we write down expressions for lines in 3 dimensions? So what do equations for lines in 3 dimensions look like, right? And it turns out to be a lot more complicated than in 2 dimensions. So here's the idea. Here's the idea that we're going to use, okay? And it's going to look like the idea that we used last time for writing down equations for lines in 2 dimensions. Remember last time we derived equations for lines in 2 dimensions using vectors. Well, we're going to derive the equations for a line in 3 dimensions also using the idea of vectors. All right. So I hope in this picture that looks like a line in 3 dimensions, right? Okay. Here's the line. Here's the line that we're at now. Okay, so just some line there in 3 dimensions. I don't want to make it parallel to one of the XY plane or the XZ plane or YZ. That sort of takes some of the fun out of it. So just have this general line here, somehow positioned, oriented there in three-dimensional space. Okay, how does it look like that? How does it look like that line is running, like it's running from? I can't tell. Is that? But it's running from this quadrant over this quadrant, right? And it's kind of coming at us, but I don't. That illusion is kind of missing. It's kind of coming. We're sort of hovering up here, like sort of as it cuts their space. Okay. Now, here's what we need to know, however, to efficiently write down equations for this line. Okay. We need to know a vector that is parallel to this line. Right? A vector that is parallel to this line. Now, that would be easy to compute, right? You could easily find a vector that's parallel to this line if you knew 2 points on the line, correct? Okay, so if you knew 2 points on the line, right, you could find a vector parallel to that line just by finding the vector between the 2 points, correct? Okay, that vector between 2 points on the line has got to be parallel to the line, correct? Because that vector is just runs right along that line, correct? But let's imagine that I'm not given 2 points on the line, but I am told, I'm told beforehand, here is a vector that is parallel to, okay? So not going to specifically state 2 points off of, but instead I will tell you here's a vector parallel. So this vector v, I'm telling you, is parallel to this line. So what are the components of the vector v? Well, let's just say those 3 components are A. So this vector v parallel to this line. All right, now, armed with that information, I can now write down equations for this one. Okay. How can we do that? We're going to do it exactly like we did in 2 dimensions. Now, you probably forgot already from last time how we did some 2 dimensions, but what I'm going to do here is exactly what we did last time in 2 dimensions. Because, look, so let's think about writing down the equation now, or equations for this line. Okay, right now I do have to know if there's 1 point on the line. Okay, so I have to have some information about the line, right? Other than it's parallel to this vector, okay? Because there are lots of lines in 3-dimensional space that are parallel to this vector, correct? And you can have this line over here, and you can have this line way up here, and the line up here, right? So there are plenty of lines, infinitely many lines, right? In 3 dimensions that are parallel to this given vector. So you got to narrow it down a little bit and get specifically to this line that you're interested in. So you do have to know at least 1 point on the line, right? Because otherwise the line can be anywhere and still be parallel to this vector, right? So you do have to know 1 point on. But look, if you know 1 point on the line, let's call that point, right? Then let's imagine we have any other point at all on the line. Okay. By the way, here are the coordinates for this point, right? P. So this is the point we know, right? This is the given point. So we know those 3. Those are given, right? But let's imagine we have any other point on the line. Now, this other point on the line, its components are unknown, all right? Because I'm saying this is any other point. So this point could be way up here, or this point could be way down here. It's just some other variable point on the line, okay? So I'm going to call that mystery point Q. All I know is it falls on this same line L that contains this point, right? So I don't know the components of, I don't know the coordinates of the point Q, right? So So let's just say they're X, Y, and Z. I don't know, folks, exactly what the values are. But look, if I compute the vector between this variable point, right, and the point P, so if I compute that vector, it has to be parallel to this given vector P, right? Because that's what I stated at the beginning. This line has to be parallel to this given vector P. But let's do those calculations then. Those calculations are so easy. So let's find this vector between this given point P and this variable point Q, which is some other point on it. Right? So let me see. Oh, here it is, right? Is it? If you want to find this vector, right, would take what? The difference in the x coordinates, right? So that would be x minus x1. And then you would take the difference in the y coordinates, right? That's y minus y1. You would take the difference in z coordinates. That's z minus. Oh, so this is the vector PQ, right? That's the vector PQ. Let me fill that in. So there's the vector PQ. And we said, what do we know about PQ? It has to be parallel to what? The vector V, right? Has to be parallel to the vector V. Now, you know what makes vectors parallel. How do you test if two vectors are parallel? They have to be scalar multiples of each other. Yeah, that's the most straightforward way of thinking about it, right? One of them has to be scalar multiple. What's the more sophisticated? What's the more fancier way of testing? Well, same slope, but in 3 dimensions, say that the idea of slope. So what? But yeah, the cross product equals 0, right? Okay. But I'm not going to try to give cross products here. That's right. So let's think of things. They have to be scalar. So that means if you take some scalar, right? So this is a number, some number t, and multiply it by the vector v, right? This is the vector v. You have to get vector q, correct? Right? So these vectors have to be scalar. I'm not sure what this scalar is, but there has to be some scalar here t, right? Okay, that you can multiply by vector v and get vector q. See, it's just that easy. So what does that mean? Oh, I think that means that the following. Let's write it down here. So if these two vectors are the same, that means x minus x1 has to be the same as t times a, right? And now if you solve that for x, you get x is equal to t times a plus x1. You get this equation, right? And if you do that for the other two components, second component and the third component, then you get these two equations. So I'm not going to write that down. So tricky. To get these two equations. Those 3 equations then are the way you can find this line in 3-dimensional space. Oh, that's kind of ugly. Notice how many equations here you have to write down to create a line in 3-dimensional space. 3. Okay. One equation for x, one equation for y. C. All right. So I claim that these 3 equations are fine. Create this line and create this line. Space. So how do we find other points? We know this point is on the line, right? So how do we create other points on this line? This line has lots of points, right? But how do we create new points on this line? You just all you do is fill in different values for t. Okay? Just fill in different values for t here. and you get different. Okay. Notice here the A, B, and C are known, right? That's the direction vector. By the way, that's what that vector B is called, the direction vector. So A, B, and C, those are the components of the direction vector. X1, Y1, and Z1, those were the coordinates of what? Given point on the line, right? Okay. So to create new points on the line, just pick different values for t here. Choose any value for t. 8 points on this line. By the way, if you take t equals 0, which is an option, that's the easiest option, right? Shows t to be 0, then all of these terms would drop out, and what we get, what point on the line? We get the original point, okay, x1, y1, z. But if you pick t to be 1 or t to be -1 or 2 or -2, you start getting new points, different points on that. Okay. These are called the parametric equations. There are 3 of them, so it's equations, right? Plural. These are called the parametric equations for, right? And so, you see already, right? Lines in 3-dimensional space are not as easy as lines in 2-dimensional space. In 2-dimensional space, you only need one equation to define a line, okay? But in 3-dimensional space, you need 3 equations to define the line, okay? Fortunately, we're not going to be working with lines that much in 3-dimensional space, okay? But that's how lines work in 3-dimensional space. When we deal with lines in 3-dimensional space, we'll usually be dealing with vectors instead of lines, okay? All right. Now, I want to show you one other thing. Let me see if I'm ready to do that yet. So all of this is what I just told you in the notes. That's summarized there in those pages. All right, let's see if we can do this. Let's see if we can do this problem today. So here we have the parametric equations for a line. Okay, those are the parametric equations for a line. You have x equal to some number plus some multiple of t, right? Y equal to some number plus some multiple of t. Z equal to some number, in this case 0, plus some multiple of t. All right, and I want to see if we can plot this line. So really, what we have to find are 2 points on the line, and then just try to draw a line between them. Okay. We could also do this in a little bit a different way by finding 1 point on the line, finding the direction vector, and then trying to draw out from that point parallel to the direction vector. Okay, that's your second option. First, let's find a point on the line, though. So, what is 1 point that's on this line? So, how can you find 1 point easily off this line? Yes, 4, -2, 4, -2, and 0, right? Okay, that is equivalent to setting t to 0 in these parametric equations. So remember, you can choose t to be any value that you wish, okay? And so if you choose t to be 0, you immediately get this point, okay? 4, -2, and 0. Let's try plotting that one, because that point is on the xy plane, right? Because its elevation is 0. Its z coordinate is 0. So we can plot that point really easily on the xy plane. If I can find it here. So this is, I think this is 4. And then what, -2? Is that down here? Yeah. Okay, so that's the intersection of that line with the xy plane is right there at the point 4 and -2. So I'm not sure what the direction of that line is yet, right? But it's going to cut through the xy plane right there at 4 and -2. So maybe it goes up, or who knows, right? Okay. All right, now So to finish plotting the line, again, you can do this in a couple of ways. One is just find another point on the line and then try to plot that point and then try to draw the line in 3D space, which is not easy, but well, I mean, I guess it's easy, but may not always look nice. So draw the line in three-dimensional space, right, that connects the 2 points. Okay, that's one choice. The other choice is to find the direction vector and try to plot a line coming out of this point that has the same direction as the direction vector. What is the direction vector here, by the way? Let's call that, well, let me just write it out. So what is the direction vector for this line? Those are going to be the coefficients of the t in the parametric equation always. So it's easy to find the direction vector. Just read the coefficients of the terms with t in them in the parametric equations. So you get what, 2, and then what, 2 again, and then 3. So there's the direction vector. Oh, so if we start from this point and we go in this direction, that should bring us to another point on the line. Let's see, can we do that? So I need to go what is this telling me? What's this direction vector telling me to do? What? Go down the x-axis 2, right? Correct? And go what? Up the y-axis 2? So wouldn't that take me here, right? And then what? Up 3? This is always the hard part, right? So up 3, maybe up here. Okay. And there's the second point on the, there's another point on the line. And then you can try to, connect those points with a straight line. That line looks like it's in the, but then the perspective becomes weird, right? That line looks like it's in the plane, but it's really not in the plane, right? It's really supposed to be what? Hovering above this point, right? Is that right? No. No, I did it wrong. Yeah, it should be right. It was really this point that it was above, right? Yeah. Okay. So that point is really elevated, right? Above, supposed to be 3 units. I don't know if this is 3 units, but it was supposed to be 3 units above the XY plane. Well, that helps a little bit. Helps a little bit drawing that vertical line to give a feel for what that line looks like. Okay. Now, if you didn't want to use the direction vector, of course, you could have found another point on the line. Here's one point on the line. How could you find another point on the line? Just by doing what? Picking different values for t, correct? Okay. So, you could have picked a different value for t other than 0. If you pick 0, you'll get this point, right? But pick a different value for t other than 0. That would give you a second point. Let's let t be equal to -1 just for fun here. And what point does that give me? So if t is -1, I will get what? 2? Am I going to get this point? Not quite, right? -4 and, am I doing that right? -3? Okay. So that point is apparently also on that line, right? So you could have plotted this point and this point and then try to connect them with a straight line. And hopefully you'll get something that looks like it that falls on this line, right? Okay. But that's hard to check in. That's hard to check in 3 dimensions. Now, there's another way of writing down equations for a line. Okay. So these are called the parametric equations. But we have an alternative way of writing down the equations for a line. And these are called the symmetric equations for the line. Let me show you how that works. Take your parametric equations and solve each equation for t. So if you solve this first equation for t, and do it quickly here, you notice you're going to get x minus 4 over 2. And then here, you would get what? Y plus 2 over 2 is equal to t. And then here you would get what? Z over 3 is equal to t. Is that right? So solve these equations for t. And since each one of these expressions on the right-hand side is equal to t, that means all these three expressions are equal. So you can set them equal to each other. So x minus 4 over 2 is equal to y plus 2 over 2 is equal to z over 3. These are called the symmetric equations for the line. Okay. It gives you the same information as the parametric equations. Okay. Gives you the same information as the parametric equations. It's just expressed in a little bit different form that doesn't involve that fourth variable t. Okay. It only involves x, y, and z. Some people find that preferable. So we don't have to introduce that extra variable t. I think the parametric equations are much better. So this is called the symmetric equations. So from the symmetric equations, notice it's the denominators of the symmetric equations. The denominator, right, of the expressions in the symmetric equations, those are what correspond to the direction vector, okay? Those are what correspond to the direction vector. And then these numbers that are added and subtracted, these numbers that are added and subtracted from the x and the y and the z, those you can use to produce 1 point on the line, okay? So you can see that 1 point on this line would be 4 minus 2, and since this is z minus 0, 0, okay? The reason I say minus 2 here and positive 4 here is you want to think of your symmetric equations in general like this. That's in general what the symmetric equations for a line look like, where a, b, and c are the direction vector, and x1, y1, and z1 are a point. Okay, yes, Petit. The denominators in the symmetric equations correspond to the direction vector. So if you pull off the denominators, they will give you the components of the direction vector. And these values that are subtracted from the x, y, and z, those will give you a point on the some point on. I think I've got this in the notes. I think I have this summarized. Oh, there it is. Okay, so they're in general are what's called the see it there. Okay, there in general is what the symmetric equations for a line. X minus x1 over a equals y minus y1 over b, z minus z minus c. A, b, and c are the direction vector components. X1, y1, b1, those are some point. Okay. Remember, you need all three parts of the symmetric equations. Okay, you need all three parts, just like you need all three parametric equations. Also, fine. Okay. Let's try another one then. I'm not sure if we'll graph this one, but let's see if we can just figure out the information that we could use to create the graph. Okay, so what is the direction vector here for this line represented by these symmetric equations? What is the direction vector? So what kind of is the direction or slope? Direction vector kind of corresponds to slope. So what's kind of the slope of this line? You just read the denominators off of the symmetric equations. This denominator is 1. Think of it as being divided by 1 if it's missing. So what do you have there? What are the components? 2, 1, 2, right? And what is a point on the, what is some point on this line? These you get from the constants that are added are subtracted from the x, y, and z, right? So what do we have here? X minus 1, that means one point on the line has x coordinate 1. This is y plus 3, so that y coordinate would be minus 3. You want to think of this as y minus a minus 3. And then this third coordinate for that point would be minus 1. You want to think of this as z minus a minus 1. So this line contains the point 1, minus 3. So 1 on the x-axis, minus 3 on the y-axis, and then down 1. So this is going to be below the xy plane. A little bit below the xy plane. That's just 1 point on the line, right? Okay. So we can't graph the line yet because we only got 1 point, right? But what's the direction? From this point, right? There's the direction vector, right? 2, 1, 2. So what's another point on the line? If you go this direction from this point, what's the second point that you would get to? So start here at 1, but go along the x-axis 2. So that would bring you to what? 3. And then start at minus 3 on the y-axis, but go 1 on the y-axis. So that brings you to what? Minus 2, right? And then start at negative 1 on the z-axis and go 2 units up on the z-axis, right? So that would bring you to 1. So you see here's a second point on this line. Let's see, what point is that? So 3, right, on the x-axis and minus 2 on the y-axis and then up 1. Gonna look like maybe about right here. And now connect these 2 points with your nice straight line, right? So see that point is going below the xy plane, right? And then it comes up and pierces the xy plane somewhere right here, about right here, right? And then it goes above the xy plane. How can you figure out where it crosses the xy plane? Oh, you think it's going to be halfway? I'm not convinced of that. So somewhere right there, and that may be true, Elijah. I'm just not certain of that. So somewhere you're thinking right about there, halfway? Yeah, that would be where z is equal to 0, right? Okay. That would be where z is equal to that would be where z is equal to 0, right? Oh, but that tells us something. Correct. We want where z is equal to, Yeah, right. So solve the equation for when z is equal to 0, but um notice you don't have just a single equation here, right? Okay. So how do you, I mean, if you set z is equal to 0, I'm down with that. But notice what you end up with here. You end up with x minus 1 over 2 is equal to y plus 3 over 1 is equal to, if z is 0, you get 1/2. So my question is, what do you do with this, right? Because you still have this 1/2 here, right? So, and so now you got these two equations, right? How do you massage those, right, to figure out how do you massage those to figure out what the x and y have, right? The ideas there. What do the parametric equations for this line look like? Maybe that would be easier. So what do the parametric equations for this line look like? So if you convert this back to parametric form, what does it look like? Remember, in parametric form, you have x, y, z is equal to, right? And then you have your point on the line, right? Okay. What's our point on this line? What are the coordinates for the point that we know is on the line here? 1, -3, and -1, right? Plus, and then you have always t, right? Times something. What do you multiply the t by? The direction vector. What's the direction vector? 2, 1, 2, right? Okay. So you can clean that up a little bit, but there's the there's the uh, there's the direction vector. I mean, there's the parametric equations for that line. Oh, maybe that's helpful because we know at this point where it crosses the xy plane, what has to happen there? Z has to be what? 0. So if I plug 0 in there, I would get 0 is equal to -1/2 plus 2 times t. Oh, but that tells me something. Doesn't that say t is equal to 1/2? T is equal to 1/2, right? Oh, but now you can plug that in, right? To these two equations to get, can't you get x and y that way? If you plug t is 1/2 in there. Well, if you do that, you would get what? The x, what would the x be equal to? If t is 1/2, you get 1/2 times 2 is 1, plus 1 is 2. So we get there 2 for x, and then this is a little bit messier, right? We get what? 1/2 times 1 is 1/2, and then -3. So that's what? -5/2. Oh, so so there's the point. 2 -5/2 and 0. Is that where you said? Is that where you said a lot? Yeah, you're pretty pretty darn close, right? Okay, there it is. Yeah, I think we in our picture we got it pretty good, right? So where it crosses the xy plane is 2 -5/2 and 0 for z, right? Not 1/2, right? 0 z. Okay. Ah, all right. Well, that was kind of a little bit of a detour there. Let's try another one. We don't have to graph it, but let's just see if we can write down the quickly there. Let's see if we can write down the equations, either the symmetric equations or the parametric equations. It's fine. All right. So this one is very straightforward question. This is just the sort of question that the homework will begin with. You have a line that passes through this point and is parallel to this vector. So that means this can be used as a direction vector, right? And once you know the direction vector and the point that the line passes through, it's so easy to write it down in either parametric form or symmetric form. Let's write it in parametric form. I always find that more useful. So in parametric form, we would have what? X equals to your point on the line, right? So start with that, the x coordinate of the point on the line, and then your x component of your direction vector times t. So you would have x equal 1 plus 2t. right? And then y would be equal to what? Minus 2 plus 4 times t, okay? And then z would be equal to 4 minus 4 times t. So there are the parametric equations for that line. And you get different points on the line by choosing different values for t and just filling them in different points. So when t is equal to 0, you get this point, but choose other values for t and you'll get other points on this line. Well, I've got so many examples here. Oh, good. This is the last one. Let's do this one quickly. Again, we don't have to graph it. We do not have to graph it. I just want parametric equations for the line that passes through these 2 points. Wow. So there is an intermediate algebra problem, except translated to 3 dimensions, right? Okay. In intermediate algebra, you be asked this question all the time. Oh, what's the equation for the line that passes through these 2 points? And you know how you do that, right? In 2 dimensions, you have to find what the slope, right? Okay. So you start off by finding the slope, and then it's very easy. You just use, since you have a point that is on the line, right? You just use the point slope form to write down the equation for the line, correct? Okay. So students struggle with that, right? Okay, but you guys learned that very well. It's just a parallel process. Maybe I shouldn't use the word parallel or anything, but it's just a similar process here in 3 dimensions. But you don't find the slope, right? Instead, you find what? What's equivalent to the slope in 3 dimensions? The parallel vector, right? You find the direction vector, right? So you find the direction vector, and then once you have the direction vector, then that's really all there is to it, right? Because since you know a point on the line, you just write down the parametric equations automatically, right? Same as in 2 dimensions. So computing the direction vector is only the only tricky part, and that's really even easier in 3 dimensions than it is in 2 dimensions, right? Okay, because we don't have to do any division in 3 dimensions. Wow, I just thought of that. So what's the direction vector here? Well, just take the difference in the coordinates, right? 1 minus a minus 2, right? 1 minus minus 2, and then what? 3 minus 1, and then what? 5 minus 0. So we get there 3, 2, 5 for the direction. And then the parametric equations would be what? X equals to, you can use this point or this point, minus 2 plus what? 3 times t. Y is going to be 1 plus 2 times t, right? And then z is going to be, what is it? 0 plus 5 times t. So you would just get 5t there. No, just that easy, right? So the symmetric equations are easy to write down, also easy to write down, right? You would have x minus a minus 2, you're using this point, over 3 is equal to y minus 1 over 2 is equal to z minus 0, which is just z over 5. So there's the symmetric equations for that straight line. Okay, now that brings us to really, as I mentioned, lines are not going to be all that crucial to us in the course, but what's really going to be crucial are planes. And so we need to get back to planes. So how do we define, how do we write down the equations for, it actually turns out to be just an equation. So how do we write down an equation for a plane in 3 dimensions? Okay, so a plane is like the easiest surface, right? In 3 dimensions. You can imagine much more exotic surfaces, right, in 3 dimensions, but plane is like the simplest surface in 3 dimensions. So that should be the easiest one to write down an equation for, right? Okay, so and it does turn out to be really simple. So let's take a break here before our brain explodes. And what we're going to do now is talk about planes in 3 dimensions, but it's going to start similar to lines in 3 dimensions, but it's going to end up simpler, okay, than lines in 3 dimensions. So planes in 3 dimensions, sort of paradoxically, are actually easier to work with than lines in 3 dimensions, and that's good because in 3-dimensional calculus, planes are sort of going to replace what lines were in 2 dimensions. Remember, in 2 dimensions, in the calculus of 2 dimensions, you were looking for tangent lines, right, to curves. So in 3 dimensions, we're going to be looking for tangent planes to surfaces, okay? So what we'll be doing is analogous to, in 3-dimensional calculus, will be analogous to what we were doing in 2-dimensional calculus, except we'll be dealing with planes and surfaces instead of lines and curves, all right? Okay, so here's how you can define a plane in 3 dimensions, okay? So you do need to write down the equation for a plane. Notice it's equation, not equations. So see, that's already easier, right, than lines. So to write down the equation for a plane in 3 dimensions, well, of course, you do have to know a point on the plane, right? So you're not going to get anywhere without knowing a point on the plane. So you have to know a point on the plane. But now you can't say you cannot say I need to know the direction of the plane, because planes go in multiple directions, right? They go in infinitely many directions, right? Okay, not like lines. A line has a single direction, but planes extend in infinitely many directions. So it doesn't make sense to say I need to know the direction of the plane. Okay, but so what we substitute for the direction of the plane is what we call the normal vector for the plane. And the normal vector is the vector that's perpendicular to the plane. Okay. It turns out if you want to specify a plane, okay, if you can specify the vector that's perpendicular to the plane, that will completely describe the plane, as long as you know a point on the plane. Let me show you why. So let's take a picture here of this situation. So that pink surface there, that's supposed to be a plane, okay? And we have to know a point on the plane, all right? Just like if we want to write down the equations for a line, we have to know a point on the line. So we have to know a point on the plane. So here's the point that I know on the plane, all right? I'm going to call that point P. So its coordinates we have to know, all right? Now, if you know also a vector that is perpendicular to the plane, notice that that's going to tell you what the plane looks like, right? Okay, so imagine my hand here is a plane, right? Okay, a flat surface in 2 dimensions. Right. Well, of course, flat surfaces in 3 dimensions can be oriented and they can be tilted, right? In lots of ways. Okay. So even if we knew a point on the plane, that by itself wouldn't define the plane, right? We have the same point in you can keep the point fixed and rotate the plane at different planes. But if you know a vector that's perpendicular to the plane, notice that completely tells you the tilt or the orientation of the plane. So if you know a vector that's perpendicular to the plane, there's only going to be one plane, right, that's perpendicular to that. Okay. So you couldn't have the plane sitting like this. So that wouldn't be perpendicular. Or you couldn't have the plane sitting like this. That wouldn't be perpendicular. There's only going to be one plane that's perpendicular to that. So that, right? Now, you have to know a point on the plane, right? Because you move the plane, slide the plane like this and still keep perpendicular to the vector. But once you specify point on the plane, then that completely goes down what plane you're talking about. So it's only going to be one plane that contains a given point and is perpendicular to a given vector. So imagine that you know here a vector that's perpendicular to the plane that you're discussing. So this is kind of, it's not really the direction vector of the plane, right? But it does kind of nail down what the direction of the plane is, right? So again, this plane is perpendicular, this vector is perpendicular to the plane. Perpendicular vectors are often called normal vectors. So we will describe this not as the direction vector of the plane, but the normal vector of the plane. All right, so that we have to be given. All right, but with those two pieces of information, I claim, we can write down the equation for that plane. All right, so here's how we're going to do it. All right, look. So imagine we have another point on the plane. Okay, so this is the given point, right? This is the given point. Okay, and so suppose we're thinking of some other point on the plane. So it could be down here on the plane, or it could be up here on the plane, right? Okay, or it could be over here on the plane. This point Q could be in lots of different places on that plane, right? That's a variable point. So, you know, it could be up here, or it could be over here, right? Okay. But in this drawing, we've drawn it down here, okay? So we have this variable point Q, this fixed point that we're given P, and this is fixed. This normal vector is given, all right? That's fixed. Now, look, if you find the vector between your given point and your variable point, so here's the picture of that vector that the book drew. Okay, of course, if the point were over here, the vector would look like this, or if the point was up here, the vector would look like this, right? But if you find that vector between your given point P and your variable point Q, that vector, of course, is going to fall in the plane, right? Okay, that vector is going to fall in this plane because this point Q is also in the plane. All right, now, if this vector falls in this plane, notice it's got to be perpendicular to your normal vector. Any vector that is in this plane is going to be perpendicular to the normal vector, the vector that's perpendicular to the entire plane. Okay, so this vector, you know, is perpendicular to your normal vector. All right, let's calculate now. Let's calculate here this vector that's in the plane. Here's the normal vector because that's given, right? So that's A, B, and C. But let's calculate this vector between this point P and this point Q also in the plane. So that's the vector PQ, right? And so what are its components? Well, you just take the difference, right? In the coordinates, right? So you get x minus x1, looks kind of familiar, right? You get x minus x1, I didn't leave myself enough room here, y minus y1, and then, of course, the third coordinate there, the third component, I mean, is going to be z minus z1, right? So that's what that vector PQ looks like on paper, right? There's a picture of it, but there's what it looks like in component form. All right, so again, this vector has to be perpendicular to the normal vector that we're given. But how do you test to see if two vectors are perpendicular, not parallel, but perpendicular? What's the easy test? Dot product. Oh, so here's where the dot product really is useful to us, okay? Well, we've used it a lot of times already, but here's one place where it's especially useful. So if you take the dot product of the normal vector and this vector, what does it have to come out to be? 0. So there it is written down, okay? So the normal vector and the dot product of this vector PQ has to come out to be 0. Well, let's expand this equation then. So let's actually compute let's expand this equation and let's actually compute the dot product. Let me see if I've done it here. So if you compute, so we know that PQ dot N has to come out to be 0. Well, here's PQ, and of course there's N. N is ABC, right? So if you compute this dot product, has to turn out to be 0. Well, let's compute the dot product. So we have x minus x1 times a, right? This plus y minus y1 times b, so plus this, right? Plus z minus z1 times c, that has turned out to be 0. Oh, there it is. There's the equation for your plane. Notice it's just a single equation. It's got 3 unknowns in it. The x, y, and z are the unknowns. Remember, the ABC, x1, y1, z1, that has to be information that you're given. So those are not unknowns, okay? That information has to be told to you. So that product has to be equal to 0. That's an equation in 3 unknowns. And what degree is it? What's the exponent of the unknowns here? This is 1. This one, what? 1. This one's 1. Oh, so that's degree 1. So first degree equations with 3 unknowns in them, when you graph those in 3 dimensions, guess what? You're going to get a plane, okay? Not a straight line, but a whole plane surface, all right? So first degree equations, 2 unknowns, that's lines in 2 dimensions. First degree equations in 3 unknowns, that's planes in, not lines, but planes in 3 dimensions. So what's the A, B, and C here? These coefficients? That's the normal vector. What's the x1, y1, z1? At some point on the plane. Some point on the plane. Any point on the plane. Okay? So if you know the normal vector and you know any point on the plane, you can write down the equation for the plane. That's just like if you know the slope and any point on a line in 2 dimensions, you can write down the equation for the line, right? Well, let's try it, and then let's try making the graph too. Okay. All right. So we want to graph the plane that contains these 3 points. Graph the plane that contains these 3 points, and find its equation in general form. Do not make the graph first, okay? In this problem, I'll show you why. You can, okay? That means you have to plot these 3 points, and then you have to try to draw a line, a plane that contains these 3 points, okay? That's not all that hard to do, but let's wait until we write down the equation first, okay? All right. So look, how are we going to do this? Oh, by the way, if I only gave you 2 points, and said write down the plane that contains these 2 points, you would have an ambiguous answer because there are infinitely many planes that contain 2 points. Okay, why is that the case? Because if I only gave you 2 points, you know there's a line that contains the 2 points, right? Okay, but then you could take any plane and rotate it around that line. And that plane would contain 2 points, right? So notice that's a possibility. So you would implement solutions if I gave you that question. But if I gave you 3 points, there's only going to be 1 plane that contains them. Right? So your intuition tells you that, right? If I give you 3 points, as long as they're not all on a straight line, if I give you 3 points in 3-dimensional space, there's only going to be 1 plane surface, right? That contains those 3 points. All right, so let's see if we can figure out what that equation is. Okay, look, write down 2 vectors. So write down the vectors that connect these 3 points. What do I mean, the vector that connect these 3 points? Okay, write down the vector that connects these 2 points. Okay, let me call this point, for easy reference here, let me call this point P, and let me call this point Q, and let me call this point R. All right, so let's find the vector from P to Q. All right, the vector from P to Q. Well, that's so easy to do, right? So that's now trivial for us. What is that? -2, 3, 0? Is that right? Did I do that right? 0 minus 2, 4 minus 1, 1 minus 1. And now you could also find the vector from Q to R. That would also work, but let's find the vector from P to R since I started with P for this vector. Let's start with P for the second vector as well. So what would I get there? From P to R. So that would be what? Minus 4. Is it 0, 3? Am I doing that right? For some reason that reminded me of something. So did I get this vector correct? Say something. Scream. Is that the right vector? Yes. Okay. All right. So these two vectors now fall in these two vectors now fall in this plane. Okay. I don't think they're parallel to each other, are they? No, they're not parallel to each other, right? Okay. And these two vectors, if they're parallel, I got a problem. But these two vectors are not parallel to each other. Okay. They're not parallel to each other, and they fall in this plane. Now, to write down the formula for the plane, the equation for the plane, remember, you need a point that's in the plane. Well, you got lots of points that are in the plane, so that's not an issue. But you also need to know what? The normal vector, the vector that's perpendicular to the plane. But that vector is going to be perpendicular to these two vectors, which are in the plane. Now, how do you find, gee, this is reminding me of something. How do you find a vector that's perpendicular to two given vectors? Cross product, right? Oh, so cross product is going to give me my normal vector. The normal vector does not have to be a unit vector, by the way. Okay, although frequently we make that request, okay? But in general, the normal vector does not have to be a unit vector. So the normal vector, we're going to label that usually N, is going to be the cross product of these two vectors. See how now cross product is coming to our rescue here, all right? It's going to be the cross product of these two vectors. And once you've got the normal vector and a point in the plane, then you're done. It's so easy to fill out the equation. Let's write down the, let's see if we can do the cross product here really quickly. So let's see, IJK, and then what? Minus 2, 3, 0. Love those zeros, right? When we're doing cross products. That's a 0. And then minus 4, 0, 3. So let's see, what are the coefficients in that? What are the coefficients in that cross product? So wipe out this column, so you get what? 9 minus 0? Is that right? 3 times 3 minus 0 times 0. Then wipe out this. Don't forget you're subtracting this one. So wipe out the middle column, so I get what? Minus 6 minus 0? Minus 4 times 0 is 0, right? Times j, and then plus, and what's the last coefficient there? So knock off this column, and you get what? 0 minus a minus 12? 0 minus a minus 12 times k, right? So that looks like what? 9i plus 6j, no, is it plus? Yeah, plus 12k. So there is your normal. There's your normal vector, or a normal vector. There are lots of normal vectors, right? Okay, any vector parallel to this one would be a normal vector. But that will do as a normal vector. So what's the formula? So easy to write down now. The formula for the line. We can use this first point. So you would have what? Take 9 times x minus 2 plus take the 6 times y minus that coordinate 1 plus the 12 times z minus this z coordinate 1, or you could use these other points as well, right? And all that adds up to what? 0. Okay. So there is the equation for there's the equation for this line. Now, if you want to plot it, the reason I said find the equation first is I think it, well, let's see what's going to happen here. We may, this may not work well in this case. I think it's easier to find the intercepts to make the plot of the, to make the plot of a plane. So when I mean the intercept, the Z, where the plane crosses the Z axis, where it crosses the Y axis, and where it crosses the X axis, plot those points, and then try to draw the plane containing those 3 points. But let's see, maybe those points are going to be out of the picture there, so we may not be able to draw a good graph. How do you find the intercept? So how would you find, for instance, the Z-intercept? Yeah, set 0 to X and Y, right? Does that cause me problems here? Probably it does, right? Then I get a really strange Z-intercept. Let's see. So you would have 9 times 0 minus 2 plus 6 times 0 minus 1 plus 12 times Z minus 1 is equal to 0. So this is what? Minus 18 minus 6 plus 12Z minus 12 is equal to 0. Oh, maybe that's not so bad. Okay. So I get 12Z is equal to, is it 30? Oh, positive 36. Yeah. Okay. So I got the sign right, but I didn't do the addition right. Okay. Yeah, this is minus 24 minus 12 is minus 36. Put over here. Oh, so we get what? Z is equal to 3. Okay. Well, that one's nice. Okay. So Z is equal to 3, right? So you got 3. We have just enough time to finish. Let's do the other two. I'll do the Y and the Y intercept. You guys do the Z intercept. I mean, sorry, the X intercept. So you guys do the X intercept for me. Hopefully it'll come out as a reasonable number that we can plot here. So y'all doing the X intercept. I'll do the Y intercept here. Did y'all get that X intercept? What does that turn out to be? 4? Oh, perfect. So 4 right here. So that plane contains those 3 intercepts, right? So if you connect those, that triangle is part of the plane. So y'all get a feel for what that plane looks like. So you can see it's kind of tilted like this, right? Okay. And runs through those 3, runs through those planes. So there's a little picture of a little piece of that plane that's enough to get some people right, or enough to give us a feel for what it looks like. Okay. So wow, we learned 2 really important things today, but they're very similar, right? So we learned how to write down equations for lines. That's a little bit icky because how many equations do you end up with to define a line in 3 dimensions? 3, right? And so we can put those 3 equations in 2 forms, right? There's the parametric equations and the symmetric equations, right? And from both of those, right, you need the direction vector for the line and a point on the line, and you can write down either the line in parametric equation form or symmetric equation form, right? For planes, it's easier. Okay, you end up with a single equation, just a single equation, right? First degree equation in 3 unknowns. And but what knowledge do you need beforehand to write down the equation for a plane. You need to know the normal vector, right? A normal vector, any vector perpendicular to the plane, and then, of course, what other piece of information? What? Yeah, you always need to have a point on the right. So a point on the plane and the perpendicular vector to the plane, not the parallel vector to the plane, but the perpendicular vector to the plane. And you can write down the equation for the plane in what's known as, I think that's general form. It's either no, maybe standard form. I don't know. I think it's standard. Forgot. Okay. All right. And so the converse of this is when you see again an equation in 3 unknowns, but it's first degree, then you know that corresponds to a plane. So when you graph that, you're going to get a plane. All right. You just have to figure out, of course, what the plane is, but you know you're going to get a plane when you see a first degree equation in 3 unknowns. Okay. All right. Well, that's we made good progress today. All right. So we also made use of our dot product and our cross product. Okay. So that was nice. Also, all right. Next time we're going to pick up some. We'll do a little bit more practice with planes, but then we're going to look up some more specialized topics in planes. Like how do you find the angle of intersection between 2 planes? So, planes are not parallel, they go to cross each other. How do you find the angle between them? And also distances. So if you want to know the distance, so if you have a plane and a point, but the point's not on the plane, if you want to find the distance from the point to the plane, the shortest distance from the point to the plane, how do you do that? Of course, we know how to find distance between points in 3 dimensions. That's just the distance formula. But the distance from a point to a plane, how do we do that? Okay. And again, our vector operations turn out to make all these problems, which seem like difficult calculus problems, turn out to they simplify those a lot. Okay. All right. So let's stop there. Let me finally stop talking there. And so you got a homework due Monday, but I'll see you it's on cross products. I'll see you guys on Monday.